So, now it's time to talk about Advanced Computational Design, our project. I'm now happy to give you a short overview of our project. And this is a project that is funded by the Austrian Science Fund in the SFB program. These Spezialforschungsbereiche or special research programs. It includes 6 sub-projects from TU Wien and 1 each from University of Innsbruck and TU Graz. And in this, and after this overview, you will see details on some of the selected sub-projects presented by 4 PhD students of the SFB. So in this project, we want to fundamentally change the field of architecture, engineering, and construction. So this field has an enormous impact on the society and the environment, but unfortunately it currently lacks the computational design tools to face upcoming challenges, although you have seen a lot of computational design tools coming up here already in this symposium. In particular, right now we live in times of extreme urban growth and limited resources. For example, Vienna, the city here, is forecast to grow by the size equivalent to the city of San Francisco in the next 30 years. And some flagship projects, and you have seen much better ones here already in these presentations, show how architecture could contribute to solving these challenges by using renewable materials like timber or biocomposites, and combining this with lightweight construction through sophisticated geometric computations and mechanical constructions. However, architecture like this is not very common, and the reason for this is that it requires innovative design, and this in turn requires the collaboration of many different stakeholders, especially at a very early stage of the design process. And this is currently too costly and difficult, and only done for flagship projects and at enormous costs. And furthermore, the results are only prototypes, so the insights are usually not reusable or generalizable, because they are not based on basic research. So why is this so expensive? Well, the reason is that there is a lack of computational tools for collaboration, especially in the early design phase. As you've seen before in one of the presentations, pen and paper is still the norm. But this early design phase is the most important one. And in fact, if you look at the digitalization of different sectors, construction resides at the very bottom of this list, right next to agriculture and hunting. While these numbers were from 2015, nothing has fundamentally changed, as can be seen in this 2022 survey for Europe, and it's the same for many other countries. And construction is again at the lower end of sectors regarding digitization. And therefore, this sector still faces stagnating productivity and innovation. So you see this negative growth actually here for UK in this curve. And as a result, while we face these challenges of urban growth and scarcity of resources, the vast majority of AEC still uses conventional process and standard wasteful materials, causing a huge ecological impact. So the obvious solution to this problem is to create digital design tools for the early design phase. I mean, you have seen many digital design tools already for later design stages, but we are talking about the early design phase. And we use the field, and this is obviously using the field of information and communication technology, where you have seen that our dean gave in the opening address the reasoning for that. So such tools would allow real-time feedback and communication on design choices across different disciplines at an early stage of a project where there's the most impact. However, the computer scientists developing these tools, us, often lack the domain knowledge, leading to suboptimal solutions. In fact, none of the big software companies in the industry have even tried offering such tools for the early design phase so far. So this is where our project comes in. Our overall vision is to bridge this gap between AC and ICT in the early design phase through basic research in a multi- and interdisciplinary fashion, as you have already heard in the introductory address. Now, for more than 3 years, the SFB Advanced Computational Design has been developing such tools and processes for the early design phase to implement that vision. Tools that can bring disciplines together and improve the quality and efficiency of AEC. So this requires work in 3 primary areas. First, design methodology in order to provide the primary interface technology to the human designers and specialists. So we deal with the question how they input design ideas and communicate with each other, but also how to integrate computational tools from all other disciplines. And the second is visual and haptic interaction in order to provide feedback for decision support and communication at all times during this early design phase. And third is form finding, or the actual realization of design intents in actual objects that have geometric, kinematic, or physical properties. So roughly, the first area covers the input side of a design project, the second one, the output side, and the third one, the processing or simulation side. In more detail, in this area 1, we follow two complementary approaches of design methodology. On the one hand, we are working on transforming implicit design intents given by sketches on 3D drawing canvases into geometric surface models. These surface models then serve as explicit representation for integration with the computational tools. And on the other hand, we look at a more physical interaction to create variations of volumetric point clouds using machine learning, allowing the exploration of larger and more abstract design spaces. And more details on that will be presented later in this session. In area 2, at any point in time, the current state of the interaction is presented to the user as accurately as possible. On the one hand, visually, through a real-time simulation of light propagation through the scene, and on the other hand, also through the haptic sense, allowing users to experience the boundaries of architectural spaces or material properties like elasticity. So you will learn details on the robotic system we developed later on in this session. Going back to the visual interaction, this also works in a reverse sense. By specifying desired illumination properties, the simulation can be used to calculate the required illumination setup through a novel differentiable light tracing method. And we also extended the approach to simulate thermal radiation, as will be presented later in this session. In area 3, form finding, instead of deferring the complex geometrical and mechanical computations to a later stage in the production pipeline, our approach is to integrate form finding already in the early design phase. For example, the possible ways a freeform surface is discretized into panels determines the feasibility, efficiency, and cost of a construction, ultimately with an impact on sustainability. But we also go beyond static surfaces and find innovative ways to transform quad-paneled surfaces with applications to novel lighting and shading solutions, foldable assemblies, as you have seen in the first keynote talk as well. Besides geometry, looking at the structural behavior of design is essential in order to introduce new and green materials, like so-called plant-based biocomposites. For these materials, we developed a multi-scale model to simulate their behavior much more efficiently. And in particular, later in this session, you will learn how we analyze the formation of cracks in these materials. Finally, we verify theoretical results experimentally by fabricating or building them, which is really important. But also we experiment with completely new materials like clay or mycelium and their potential for sustainable construction. The properties of these materials are then analyzed again theoretically. All of these projects are tightly interlinked, of course, as presented by this connection star. And to achieve all this requires a multidisciplinary team, so it's nice. So I can introduce the people who are working on this project. So at the beginning of the project, luckily, we were all able to build on this collaboration that was initiated by Helmut Pottmann here in the form of the Center for Geometry and Computational Design, which is the symposium we are having about here. And then we extended this with knowledge in architectural design and material experimentation from University of Innsbruck and TU Graz. In total, the project encompasses 4 faculties: computer science, mathematics, architecture, and civil engineering. So I will show you now a few of the examples of how we worked together and achieved more than these simple sums of the project. So first of all, we have created a sketching platform as the central hub of all the sub-projects in the SFB. This platform allows users to sketch in different modalities, like on an iPad or in virtual reality. In particular, we have identified how architectural designers like to sketch, using different stroke types for the boundaries and the surfaces. With contributions from geometry, we developed algorithms to convert these sketches first into segmentations and then into curved networks and finally into geometric surfaces. The platform, the sketching platform, then uses these surfaces to communicate with simulation tools. For example, with lighting simulation to compute optimal lighting conditions. With structural simulation to compute stability for different material choices, and with geometry simulation to compute different panelizations or transformable variations. The platform can also convert point clouds to geometry, and all of this will be reflected in the app and shown to the designer. And in certain modes, like virtual reality, the feedback will not only be visual, but also haptic, or real, through fabrication. And again, 4 of these topics will be presented in more detail shortly. As an alternative to sketching, we also collaborated in a more immediate hybrid concept modeling workflow based on point clouds. So here a feedback loop is established between the physical and the digital modeling. Through style transfer algorithms, the user can modify the point clouds according to different inputs and create variations, and also influence the material distribution, which is only possible since the algorithms also generate the internal structure of the point clouds. And this in turn also allows evaluating the structural performance directly on the point clouds. And finally, the generated point clouds can be directly fabricated using a novel point printing workflow. And putting all these different elements together, we obtain a material-informed design framework, which equips designers with the necessary knowledge about design implications, starting from a sketch or a physical input. The sketching platform or the concept modeling platform computes a geometric or point-based model, and this can then be interpreted by a structural analysis module for overall structural feedback, and by material models, for example, our novel model for plant-based biocomposites, which provide the mechanical input parameters. The design can be visualized in virtual reality using realistic light simulation, and a novel origami structure positioned on a robotic arm allows for immediate elastic feedback on the structural stiffness. The framework also adds an important physical materialization step where prototypes of both materials and geometry are actually fabricated and presented to the user. So in summary, our overall vision is to develop advanced computational design tools and processes for the early design phase, linking design methodology, visual and haptic feedback, and form finding through basic and multi- and interdisciplinary research in order to improve the quality, efficiency, and sustainability in AEC. And this is the team of PIs last week in front of the Austrian Science Fund before we gave a part of this presentation and other presentation, and which will decide on whether we'll get another 4 years of funding. So please wish us luck. Thank you. And we'll go immediately through all the presentations. At the end of the presentations, we will have a round, a panel round for all feedback. Okay.
Yep. So hi, I'm Johannes Schluge. I'm researcher and lecturer at the University of Innsbruck at the Institute of Design Research Group ISD, Structure and Design led by Christina Schienecker and Professor Stefan Rutzinger. Welcome to my presentation, which shows a small insight of my PhD thesis in progress, point cloud tectonics, raw granular data as informed volumetric design medium. The thesis Point Cloud Tectonics is part of the research project SFB, Advanced Computational Design, and is embedded in the sub-project at the University of Innsbruck, SP3 Computational Immediacy. In our research, we aim to introduce a concept based on hybrid digital and physical design workflow for accelerated volumetric modeling based on 3D point clouds. In the video, you can see the first prototype of the hybrid workflow of building physical objects and inform them machine learning assisted digitally. Volumetric point clouds can be described as point clouds defined through their volumetric entity. Volumetric point clouds have a depth structure. They can be described by void portions, Pouchet niches, solid areas, their skin, and their signals. Volumetric point clouds describe objects from the largest particle to the smallest, starting from the whole to the single unit. They are carriers of multidimensional information, such as color and distance to neighbors, and can thus describe different conditions, which we call attributes and features. In summary, one of the main motivations of us is to apply real-time 3D machine learning assisted design workflows based on volumetric point clouds. Basically a process that utilizes unstructured point clouds as input, provide the manipulations through different trained volumetric styles, such as lattice structures using an autoencoder, and enable conceptual models with informed multidimensional features as output. The point cloud tectonics thesis builds on the computational immediacy research and connects to the hybrid physical and digital workflow being developed. The particular interest lies in considering how robotic fabrication based on volumetric point clouds informed by digital design features can encode and decode attributes that make the point clouds a design medium for volumetric conceptual models. Volumetric negotiation of point clouds is fundamentally defined by the application of filter patterns, such as the application of flexible resolutions of volumetric point clouds, raw, adaptive, and rasterized. So we negotiate with rasterizations, but see a large potential in raw volumetric point clouds. There are multidimensional local features to control and furthermore especially suitable for embedding porosities. With raw point clouds, there are more attributes and information per point, which we can define, for example, by the position of the neighboring points, the volumetric size, and the volumetric position with different densities. In our understanding, tectonics refers to the relationship between parts and the whole in order to describe a totality and thus a performance. Classic components of tectonics are columns, walls, ceilings, floors, and staircases. Such in the Domini house, you can see it on the left-hand side. Digital tectonics has raised particular interest in the age of digital fabrication, as it allows tectonics to be digitally controlled and fabricated. Especially the extension of digital tectonics by volumetric modeling creates our great interest. Here the view behind the surface begins and reference is made to the inner volumetric organization. Building on this, we would like to go one step further with point cloud tectonics. We see each point of structure as an elementary unit of the whole, which the material and the internal structure can be adaptively designed. We want to zoom into the microstructure, giving each granular and individual resolution, feature, and meaning. Continuous developments in the direct conversion of volumetric point clouds into point printing toolpaths based on informed granular data. The goal is to direct conversion of volumetric point clouds with 3D feature attributes into physical prototypes. Volumetric methods are particularly suited for the manipulation of material distribution regarding graded and combined materials in the early design phase. We focus in point cloud tectonics on sustainable materials. In the first applications, we use clay as a point printing material. To establish a definition of point cloud tectonic, we have created a large atlas of negotiation strategies of point clouds and concept models. This atlas is open to our students to adapt and extend technologies and techniques. Basic negotiation strategies are filtering of point clouds based on their densities, porosities, resolutions, colors, and describe tectonics by instances, volumetric data blocks, signed distance functions, or sphere packing, for example. Design courses in particular serve to enhance scalable scenarios and expand the atlas of point cloud tectonics and how to incorporate new concepts of dealing with volumetric point clouds as design medium. In this project, the students investigated how to establish different resolutions of the inner volumetric structure by manipulating a raw point cloud in ordered octree structures. Each cell is now considered individually to create an inner structure that negotiates between void and solid. In this project, the interest lies in how to inscribe transparencies in the tectonics of volumetric point clouds through a digital occupation and control of densities. Moreover, these ideas were materialized physically through studies of how to control the occupation of points through different densities, colors, and transparencies. In this project, the focus was to get volumetric point clouds through CT scans, which were geometrically investigated. The idea is to create tunable granular data with the adaptive scales from urban to human to the integration of nature combined with a porous idea to inscribe specialities and exposures. Furthermore, one focus is the inclusion of natural material system, here for example soil, in order to create different material resolutions at different scales, in the sense of a level of detail. In contrast to teaching, where our developed machine learning tool was not applied, we used the full scope of our design workflow described before at the AEC Summer School in Stuttgart. Our goal for the design workflow concept is to explore new architectural form-finding methods by establishing immediate connections between physical and digital design spaces, from their conceptual design to experimental prototyping. So during our workshop, we let the participants work with our hybrid workflow, which can be described by the categories build, capture, inform, and print, to prototype a series of point cloud tectonics. First, the participants began by creating designs with found objects, followed by real-time capturing and manipulation of their digital twin, the point cloud, with desired 3D styles from our trained library and the use of the machine learning tool. The informed design served as the basis for the fourth component, the process of robotic point printing. So optimization processes of the structural position of the points, as well as the extraction of the point features, the direct printing process of the point clouds could be started. In this porous structure, the transformation from digital to physical point cloud is clearly visible. To conclude, I would like to share that we're currently working on the implementation of publishing our point cloud tectonic design process and the associated interface through an interactive web application. The current status is still an early work in progress version. What can you see? What you can see on the next slide. So our goal as Outlook is to make this web application open source available next year in order to be able to upload custom point clouds within the application, which are then volumetrically filled with the 3D style transfer and can already be covered with tectonics as a preview. Thank you.
Hello everyone, my name is Christian Freude and today I will talk about thermal simulation for interactive conceptual design. This project is a collaboration between the TU Wien and the King Abdullah University of Science and Technology and was initiated by Florian Rist and Helmut Pottmann. And it builds upon a rendering framework developed by Lukas Lipp in the course of the SFB sub-project Lighting Design for Architectural Design and was supervised by David Hahn and Michael Wimmer. And first, I want to give a short motivation why the simulation of thermal radiation is important. So in many engineering disciplines, it's necessary to predict the thermal behavior of a design, for example, in the design of buildings. Modern buildings can exhibit complex facades, as illustrated by this example designed by Frank Gehry. And depending on the complexity of its shape in combination with the used materials, it's not always trivial to accurately predict the effect such designs can have on their surroundings. So for example, in the case of this building in London, designed by Raffaele Vinoli, the curved facade focused sunlight at the spot on the street where it started to melt parts of parked cars or damaged other things in the area. And the architects became aware of this during one of the design iterations, but they underestimated the problem because of the lack of tools to analyze it properly. And this problem was eventually solved by changing the facade to stronger diffuse the sunlight. But this is an example how important thermal analysis is. So for the design of our approach, we had the following design criteria. Modern designs can often include materials with complex reflection characteristics. Therefore, we wanted to support arbitrary radiation transport, including diffuse and non-diffuse reflection. So thermal effects include heating and cooling over time. So in addition to simulations which compute the steady state of a design, we also wanted to support simulations over time, so-called transient simulations. And problems with the design should also be discovered early on in the project to keep the cost of required changes minimal. And therefore, we aimed for fast simulation computation to enable quick iteration and feedback, which is necessary to support the flow in the early design process. And furthermore, we wanted our approach to be easily set up and use and be directly integrated into design tools. With these criteria in mind, we developed our approach, which we can use to simulate thermal radiation for the analysis of designs in the early phase. And here are just two teaser images showing a snapshot of a simulation over time on the left. And on the right, it shows the analysis of a heat island caused by a building, which is similar to the problem I mentioned in the beginning. And we also integrated our approach into Rhino and Grasshopper, a popular design tool for architects. Our approach sits at the intersection of multiple fields. So it was motivated by the lack of proper tools for the thermal analysis of architectural design in the early phase. And in this domain, there are many smaller tools, each for a specific subproblem. Most related ones are for computation of direct solar radiation or glare caused by reflection of the sun in windows or glass facades. What is missing, however, are tools to simulate thermal and indirect radiation globally and quickly. In the domain of digital engineering simulation, all kinds of physical phenomena can be simulated, including radiative thermal transport, using the so-called finite element method. However, here, commonly the simulations are less interactive and often only diffuse radiation is supported. And in the field of computer graphics and rendering, fast and interactive simulations of complex radiation transport was extensively studied. However, here, commonly only the steady state of visible light is simulated. And as we will see later, absorbed radiation and temperature-dependent emission is ignored. So our approach tries to combine ideas from these fields to quickly and efficiently simulate transient as well as steady-state thermal radiation. Next, I want to talk about electromagnetic radiation and how simulation of thermal radiation differs from conventional rendering of visible light. So in general, electromagnetic radiation is emitted by all matter which has a temperature above absolute zero. And only if the temperature is high enough, we start to see the effect in the range of visible light. Cooler objects emit radiation mostly outside the visible range at lower wavelengths in the direction of infrared and below. So depending on its temperature, an object or material loses energy by emitting radiation. And similarly, by absorbing thermal radiation, an object can also gain energy, which adds to its temperature. So it is this interplay of emitted and absorbed radiation which determines how the temperature of an object changes. And if it radiates more energy than it absorbs, it cools down, and if it absorbs more than it radiates, it heats up. Please note that here we only focus on temperature changes due to thermal radiation and do not consider convection or conduction or other physical processes. While our project focused on radiation, a parallel one at KAUST investigated convection in a similar context, which has been published as ANN Sim this year, called Urban Flow: Designing Comfortable Outdoor Areas. So how can we simulate radiation? As I said before, we want to use ideas from computer graphics to simulate thermal radiation. However, there's a problem. We cannot directly apply methods from classical rendering to thermal radiation. To illustrate this, let's imagine a scene with some objects and a light source. This light source emits visible light because of its temperature. However, in classical rendering, the amount of emitted energy is usually directly set to some predefined value and not derived from the temperature of the object. And to compute the illumination of a scene, this emitted light is then traced through the scene and gets stronger or weaker reflected based on the material of the object or surfaces and ends up illuminating different parts of the scene. However, two things are not considered here. First, the absorbed radiation is ignored and only the reflected radiation is considered. However, as we saw before, we need to consider absorbed radiation to determine the temperature change of an object. Secondly, in classical rendering, the emitted light is not depending on the temperature, but predetermined. Furthermore, when it comes to thermal radiation, not only light sources are emitting radiation, but all surfaces in the scene, which have a temperature above absolute zero. So in order to simulate thermal radiation, one has to not only solve the global illumination problem, as in classical rendering, but in addition also keep track of the absorbed energy and temperature globally to determine the emitted energy. So how does our approach solve this? We choose to use a finite element approach. However, instead of volumetric elements, we use surface shells with associated thickness. And we use a piecewise constant and vertex-centric approach, which means that we store temperatures at vertices and do not interpolate between vertices, but assume constant temperature around each vertex. And to compute the radiation transport, we do not use direct form factors, but instead we use hardware-accelerated photon tracing to compute full global paths on which radiation can be exchanged between elements. And like this, we can support arbitrary non-diffuse radiation and reflection. We encode this transport in an operator which enables us to quickly compute the temperature change globally. And because we choose a piecewise constant approach, we do not have to deal with complex interpolation terms, but can simply multiply this operator with all the temperatures raised individually by the fourth power. This is denoted by this dot notation. And having an efficient way to compute the temperature change, we can now compute transient simulations. For this, we use the backward Euler method, and here we also apply an important optimization. As long as the scene geometry does not change, and we can pre-compute and reuse the transport operator. This speeds up the computation of temperature changes over time significantly. However, there is still the question how to integrate changing external sources for animations. So for example, if you would want to simulate the effect of the sun and sky radiation on a building design over multiple days. The problem is that if you would choose to model the sun as a moving heat source, we would need to recompute the transport operator for each iteration because the scene geometry would change. To solve this, we instead model a sky dome as a fixed geometry, and this enables us to change the environment radiation without the need to recompute the transport operator during simulation. And this is an example for such a transient simulation over the hours of 2 days, where we can see the cities heating up during the day and cooling down during the night. For this simulation, the pre-computation of the transport operator took around 30 seconds, and each time step of 1 hour took around 1.6 seconds to compute. Next, let's look at an example where we would like to solve the problem of a heat island similar to the building in London showed in the beginning. Here you can see the Rhino and Grasshopper interface where an architect can design a building in Rhino and then use our simulation node to run the heat simulation via Grasshopper. This building design is similar to the one in London as its facade is concave, highly spectrally reflective, and therefore focuses heat energy into a small area. For this scene, the pre-computation of the transport operator took about 4.3 seconds and the steady-state solution around 9 seconds to compute. So to fix this problem, a designer can experiment with different building shapes or materials and only needs to wait a few seconds to see if the changes helped. One fix could be to change the facade material to more diffuse and scatter light. And in this case, the heat island on the neighboring building is gone. But what if for some reason a diffuse facade is not wanted or not possible? Then a designer would need to change the shape. And one alternative would be to get rid of the concave shape altogether. But this might be a bit drastic, and maybe one wants to keep the shape more interesting. A less radical change would be to add a convex element to divert the radiation, like seen here, and this also helps to get rid of the heat island. So with our approach, it's possible to easily simulate thermal radiation for different designs and analyze them in an early design phase. And to summarize, our approach can be used to efficiently simulate steady state as well as transient radiation and supports non-diffuse transport and is integrated into Rhino and Grasshopper. And our efficient thermal solver is possible to the pre-computation and caching of the transport operator, the acceleration of photon tracing via RTX hardware, and integration of environment radiation as fixed geometry to avoid recomputations. And this concludes my talk, and I want to thank you all for your attention.
Hello everyone, my name is Saroush Mortezapour from SFB Subproject 5, and today I'm going to talk about a large-scale haptic feedback in virtual reality using a collaborative mobile robot. Let me start it with virtual reality and design. In the recent years, virtual reality has become a powerful tool in the hands of the designers because it is capable of actually providing an immersive way of engaging and interaction with the models, with the design models. Virtual reality is capable of providing immediate feedback, which is very important in case of architectural design. And also with virtual reality, one can simply go beyond the visualization. It means that one can study the effects of lightings and acoustics in a construction before it's even built. Virtual reality traditionally has been focused on two main senses, visual and auditory senses. But we at SP5 took it one step further. We worked on haptic. Haptic means the sense of touch. Adding the sense of touch to the virtual reality for design means that now the designers can feel the materiality of their sketches. This means that they can gain a deeper understanding of the design models. Not only the designers can try new innovative material, but also they can experience the sensation and mechanical behavior of this material. Good news is that we are not just talking about one snapshot of a time, but with virtual reality and haptic in place, one can study and plan the entire life cycle of a construction. From the beginning, means the early stage design. This brings me to our haptic system, Cobodec. Cobodec is an immersive virtual reality haptic system with free walking support, meaning that one person, a designer, can get into the virtual environment and still walk freely in the physical environment. Then these users can really touch virtual objects. How is it possible? We use an industrial-grade cobot, which stands for collaborative robot, special type of robot, in order to present a physical prop at a physical position for the designer. Cobodec is actually a system made of so many different components and subsystems that collectively, from one side, control all the virtual environment and everything that is related to the user, tracking the hands, and on the other side, all the subsystems that help the autonomous robot to navigate in the system and function. I'm sure everyone is familiar with the term autonomous robot, but in case you don't know in the robotic background, autonomous means that the robots, that they need no interaction with the user and no intervention from a human, and they can decide and function without any human intervention. Out of all the subsystems, I want to talk about the main part that is most interesting to me. I want to share it with you. This is the major part of the brain of our robot. We call them behaviors. Behaviors are like modes in which the robot reacts differently to the surrounding environment. We actually inspected all of the different scenarios and designed and implemented 4 different behaviors for a robot. These behaviors are actually organized in a state machine structure, and the transition between the behaviors or states of the state machine happens based on the changes in the status of the workspace. These behaviors are, first and foremost, the main purpose of the system, which is haptic. When haptic behavior is activated for the robot, this means that the user needs to interact with a virtual object. Therefore, the robot needs to position the object, this haptic prop, which actually presents the whole or a partial of the virtual object for the user to encounter. In the case of the video that you can see on the right side, a virtual wall is visualized for the user, and the user is interacting with the virtual wall. And because of that, the haptic prop is given as a flat surface. But because the haptic prop is actually smaller than the virtual object, the robot needs to follow the hand of the user and move the haptic prop in order to cover the entire surface of the virtual object. But once the robot is not in use for any haptic interaction, we don't park the robot in a corner of the room, because we want to actually shorten the amount of time for the next haptic interaction. That's why we follow the user, or so-called chase the user. But we don't do this chasing blindly, because as you know, and as I have also mentioned, the user is in virtual reality, immersed, and doesn't know anything about the position of the robot. Therefore, the security and safety of the system is very important for us. That's why we use a user-centric weighted space, whose weights are determined by the function, the formula that is shown on the screen, and after calculating the weight of each point in this space, the robot needs also to consider and avoid obstacles, both static and dynamic. But with all of the measures in place, there still could be some special cases because the nature of design is unpredictable. Things, contents are created and removed dynamically, especially in case of architectural design. Therefore, the behavior of the designer is not completely predictable for us. There could be some cases that the user, the designer who is immersed in virtual reality, starts to walk toward a path that is blocked by the robot. Therefore, if we do nothing and just let the robot be there, there might be a collision between the user and the robot. In such cases, the robot uses a special behavior called escape. Our robot constantly is computing and calculating some escape routes, some routes that are safe in the environment, so in case that this scenario happens, the robot can preempt the collision by unblocking the user's trajectory. Something that is very important here is that in escape we have special requirements. That's why our robot uses a dedicated navigation system that is much more faster than the normal one that is used by the other behaviors in order to make sure that we escape the path, we escape as soon as possible for the user. But with all of the things that I already mentioned, there could be some special cases like when the robot is stuck in a corner of the room between the wall and the user, and the robot has no option to escape. In such cases, our system informs the user by visualizing the robot for the user and warning the user about the upcoming potential danger. Here in this video, you see all of these behaviors that I talked about in both simulation environment and in physical environment. For instance, here you see that how the robot unblocks the user's path. Here you see that the robot in the physical space is keeping distance to the user and following the user around. And once the user wants to interact with a virtual wall, the robot drives in front of the user and places the haptic prop at the position that is required. And if the user wants to actually explore the whole wall, the robotic arm follows the hand of the user in order to give the feeling that the user is touching a much larger surface. As you probably have guessed, we have very unique safety requirements in this system because this is officially the first time that a user and a robot, even a collaborative robot, are put into a small system, into a shared workspace, while the user is completely blindfolded and has no knowledge about the current position or velocity of the robot. Therefore, none of the relevant industrial standards work for us and cover all of the scenarios. That's why we conducted a full risk analysis and we collected some safety measures, formulated them as guidelines for anyone who wants to work on robotic and robot-based virtual reality haptic platforms. But having access to Cobodec, which is capable of positioning haptic props in different positions of the room, and at the same time having access to data from very precise force and torque sensors of the robot, allows us to go one step beyond visualizing and rendering only static objects haptically. Now we can even go toward the simulation of numerical deformation of the material. This is how it's done. That the user applies some pressure on the haptic prop that is attached to the robot measures the amount of force that is applied by the user, it does some computations in the background, and it just applies the current amount of resistance back in order to simulate the numerical deformation of this specific material. This is something that we have been doing and still doing in collaboration with other SPs, mainly our mathematicians and our material scientists. And this is, I should say that this is not the only way that we are dealing with numerical deformation. As it was mentioned before, we have very sophisticated origami-inspired end effectors and haptic props that you can see already in the exhibition. And for the sake of time, I removed them from my presentation, but I would be glad to discuss them with you in the exhibition. Based on the evaluations that we did and we published in high-ranked virtual reality conferences, Copodec brings significant improvement over all existing solutions for haptic in virtual reality in terms of flexibility, in terms of the size of the workspace, maximum force feedback that the robot can handle, versatility of the tools and shapes that it can represent. And we also have shown that our behaviors led to a safer workspace for the user, a faster haptic response time, and we could lower the amount of energy that the robot needs to navigate in the system. If you are wondering, an escape for the robot takes around 1.5 seconds from the moment that it detects that the user is unknowingly approach the robot until the time that the scene and workspace is safe again for the user. And it takes around 10 seconds after the detection of the interaction for the robot to provide the haptic feedback. Also, with our chase behavior, we saved around 25% of the energy compared to a normal park and drive approach. Here, I want to thank everyone for your attendance and for your attention. My name is Soroush Mortezapour, again from SB5, and now I give the stage to the next presenter. Thank you.
Thank you. So today I'll discuss the numerical modeling of plant fiber reinforced composites, or so-called biocomposites, and the connections we've made between mechanical insights from our research to other disciplines within our interdisciplinary research group. So first of all, what are biocomposites? In the face of rising environmental concerns, the construction sector is seeking new materials with a low CO2 footprint that are also strong and lightweight. Now, let's consider plant fibers. They are not only abundantly available, but also naturally optimized, offering high performance relative to the weight. While there's a vast natural variation in these materials, all plant fibers share the same basic components. So the quantity orientation metaphor. So cellulose acts as a long reinforcement, just as steel does in concrete. Hemicellulose are the shear rebars, and lignin binds everything together. These basic building blocks can be extracted and reassembled, or we use just plant fibers which are already strong themselves and combine them with biodegradable polymers again to build new materials, so-called biocomposites. And we envision these biocomposites to be used in future construction projects. However, this huge range of potential biocomposite combinations means we need sophisticated and reliable models to predict the material performance. There exist different methods to predict material behavior for stiffness and strength, and in this presentation here, my focus will be on the numerical modeling of strength at the microscopic level. And for these models to be effective, we need to understand first how failure in these materials work. Generally, when testing new materials, the strength of them are usually tested by just pulling them apart, where you measure the load and the displacement and plot them against each other. And the shape of a test specimen could look like this here. And if you zoom in, you can see the individual components, in this case here in gray, a natural fiber embedded in a biodegradable matrix. And this is now how the ultimate failure of the biocomposite can look like, if you pull just hard enough in this direction. And just before this failure, you may observe some micro damage in the individual components, but what exactly happens here inside? And we can now further distinguish between three main failure mechanisms. First is fiber rupture, where the fibers itself fail. Then there's matrix softening, where the glue or the polymer surrounding the matrix surrounding the fibers degrade. And then there's interfacial failure, where the bond between the fiber and the matrix weakens or breaks. Now that we know what the real world looks like, we need to find a reliable way to capture all those effects in a numerical model. And we decided to model this with a 2-fiber unit cell here, which is periodically repeating endlessly in all directions, with one fiber here in the middle and the other one split into 8 parts, but joined together again because of this endless repetition of the unit cell. So now we've made a definition of the geometry of the model, and now we try to find some laws to replicate the observed behavior of the composite. And for the fiber rupture here, we have the so-called direction separation law, which basically says if a certain stress level in the fiber point is exceeded, then a crack is initiated, and this stress then gradually decreases until the fiber gap is fully opened. And we define quite similar material laws for the other effects, for the degradation of the matrix and for the debonding of the interface. And all those damage mechanisms, they act together, some more and some less, depending on the individual components, until the biocomposite is fully torn apart. And we have now a model at hand to fully simulate just such post-crack behavior of biocomposites, which has actually never been done before. So now I want to show you how such a simulation could look like. And here I have a model where we purposely put a weak fiber in the middle to show what the model is capable of. On the left here, there's a load displacement curve as in a real tensile test. And on the right, there's a visualization of the model box, which is cut in half here to better understand what's going on inside. And on the top, you can see the stresses in longitudinal direction, and below some equivalent strains of the matrix material. So a first crack is initiated, and the fiber resulting in this load drop, but the surrounding matrix is still capable to distribute all the forces, which allows the biocomposite to bear even more stresses. But starting from this fiber crack, the matrix gets slowly damaged, and parallel to that, there's a second fiber crack growing, and suddenly the whole composite fails, where various failure mechanisms grow together here. And of course, we need to validate our model, comparing our predictions to real experiments. And here we have a stress strain curve, which is quite similar to the load displacement curve shown before. For example, with short-aligned fibers pulled in longitudinal direction. And as you can see, our model with the perfectly affine fibers matches pretty well the experiment if pulled in just this direction. And we can do a quite similar validation with long fiber reinforced composites. In this case, there are 5 experiments with different materials here shown, while pulling them apart in transversal direction. And here, with this matching color pairs here, you can see how our model matches the real-world experiments. So what is this all good for? We now have a reliable model, and we have tons of possibilities to make parametric studies or mix different materials together, which could be a very tedious task if you want to do this in the real world. Maybe we want to know if the biocomposite can get even any stronger, if you get a better bond between fiber and matrix. Does it even matter? So one question could be, how does the fiber-matrix bond influence the overall biocomposite behavior? So what happens if the interface is stronger or weaker? The upper curves here are results from the biocomposite simulations with high interface strength between fiber and matrix, and down below with low interface strength. And what happens if I shift here the slope of this direction separation law, basically meaning that we have a rather brittle or very ductile interface. And that's just one parametric study, that's just one model here. And with this, we can show that we are now able to reproduce that the fiber-matrix interface can have a huge impact on the macroscopic biocomposite behavior. And just such insights into the material can help us make better decisions when producing and designing new materials. So all of this was just one part of our research, and with our interdisciplinary partners, another main goal in our research is to help designers and decision makers to provide them feedback in the earliest design phase. And one sub-project developed this 3D sketching platform, as you've seen before maybe, and we linked our knowledge regarding materials and structures to the sketching interface. And for this, we developed a material-informed design framework, where you first have a sketch. For this sketching platform, we provide a material database with some predefined biocomposites. And this sketch has then to be translated into a suitable geometric format, which is done with a machine learning algorithm from our partners, Subproject 2, to be able to do structural simulations with the finite element method. And for this structural model, again, the material model is needed, where we specifically provided a multi-scale material model, developed also at our institute. And then with this information, you get immediate feedback. Do you need to optimize the material? Do you need to find a better geometric structure? And one quick example here, starting from an initial sketch, the algorithm translates the 3D strokes to a 3D volume mesh. The designer has to define boundary conditions, loads, and material. And then the designer gets the first feedback. The red areas here indicate that these areas are above the critical stress limit, given the structure and the chosen material. And then the designer can now redesign the structure or reiterate through different materials. Or, for example, they can even just say to align these fibers to the principal stress direction, which then, in turn, gives optimized results. So in summary, we are able to predict reliable biocomposite material behavior and link this to the earliest design phases. And in the future, we'd like to extend our interdisciplinary collaborations even further and link many other fields together in order to support designers and engineers in the earliest design phases. Thank you.
Thank you. Now I would like to call the other presenters to come to the stage as well. And as I said, we will try to do this in a kind of panel discussion or, well, panel question session. So I would like to ask you, the audience, to ask any question concerning any of the presentations so far, even including mine if you really need to. But actually it should be our PhD students here standing in the spotlight. So. Yes. Thank you for always asking good questions.
You're welcome. Maybe for me, one of the most important question is, so you came together from different disciplines, and what did you had? Of course you had, but maybe you don't. You say now no. Did you have any communication problems in telling your problems to the others and just changing your experience? And when you were working on a problem, so how did you do it?
Oh, that's a good question. Who wants to answer that? Maybe no.
Yes, I can start, actually. I have no communication problem because I have high-speed internet. But no, apart from jokes. Well, actually, we have a lot of meetings. So we get together every now and then, every month or every 2 months. And these are very good opportunities, actually, to collaborate to each other and to exchange the data of those 2 months. And if there's any opportunity of further collaborations, we actually set other meetings. So we meet other, outside of this big team in order to facilitate the collaboration between us, in order to have access to the new knowledge that we miss as some scientists. So, for instance, we come from computer science and robotics, and of course, we don't know or know very less about material science. That's why I think this is a good opportunity for all of us to actually grow in this project. So it was 4 years already, and it hopefully will be another 4 years.
It's not yet 4 years. It will be 4 years in March.
It was 3 years.
For some of us, it's not even as
3
long
years
as
and
that.
1 month.
Anybody else wants to add to that? Otherwise, I have to say, well, actually, it starts with the PIs. I mean, it took us, I think, half a year to up to a year to draft this original proposal, and we had meetings on meetings and meetings. And I still remember these meetings where we were talking about the proposal, and couldn't understand a word the others were saying. So what is a solution space? What is the design space? These had completely different meanings in architecture, in mathematics, and so on. But overall, we grew together. And I think already the fact that we as project leaders kind of understood each other made us also simpler for us to communicate this to the PhDs, and hopefully, yes. Okay, are there more questions? Back there, there's a question. I think we need the microphone, yes.
My question is for Sarosh. Thanks for the nice presentation. It was really great work. So my question is, in your presentation, you defined risk analysis because the robot and the safetiness. So how do you measure this safetiness? How do you come to conclusion? How do you make this risk analysis? So this is the safety measure for the robot not to go into that area, or how do you come to that numbers? What kind of experiments do you conduct?
Well, actually, if you're asking about the process of risk analysis, it was actually a long process. So a student helped us with a thesis, and also it was the output of many meetings that we had in order to identify the risk places in our system, that what could go wrong and what are the results. And out of this, we actually came to a list of the things that we need to consider in our system to make sure that the system is safe enough for the user. And of course, this is something that is in the process of publication. So this could be a basis for everyone who wants to do something like what we did in the system.
Okay, thank you.
So right there's a question. Now you have to ask somebody else.
I have a question to Christian about thermal simulation. The question is if the wavelengths of light matters, because I think that your simulation does not take care of that. But for example, glass behaves very differently for visible light and for long wavelengths radiation.
Yes, so at the current state of our approach, we basically just simulate the total energy, so we don't split the spectrum into different wavelengths. And our material models are also currently very simple. So we don't basically change the reflection characteristics based on wavelengths. So this can be extended, but at the moment we just have a very simple model. But also in the early design stage, a lot of materials are not so detailedly specified. So you basically want more like a coarse analysis. And of course, if you want to have these more detailed models, then you really need to measure all the materials, and this we so far didn't do. So we just used some sensible material parameters. But yeah, this is correct. We don't split the spectrum in some subbands.
Yeah, actually, if we used computer graphics, we could go to spectral simulation and simulate individual wavelengths, but then this would be hard to do in real time or interactively. Okay, more questions. I think Johannes and Valentin are still waiting for questions to be asked.
Thank you. Nice presentations. I have a question on the biocomposite. You gave an analysis of those pulling forces, those strain forces. How do those biocomposites behave if they are exposed to bending forces? And are they considered to be used as the 90% of the construction in the end, or a 10% adding to the construction in the end, or how?
You mean in terms of strength, or what do you mean exactly? The reason why I showed only this tensile test is because most of the materials tested in reality are only tested in tensile direction. But I can model, of course, I could model everything in all the directions. We're actually capable of doing that, yeah.
If I understood correctly, these biocomposites, they all have this fiber nature. So I assumed that they would behave best on tensile forces. And so my question is, are they suitable for any kind of constructions, or do they have special use cases where they are exhibited to tensile forces predominantly?
So that I would say that really depends. they could be suitable for every structure, and that really depends. You have so many kinds of biocomposite materials. You could say these fibers are very short fibers and they are randomly distributed, or they are aligned just in the direction where you need them. So if you align them in this longitudinal direction where fibers naturally are the strongest, then yeah, you could play around with this, and then it would be possible for all structural imaginations. Yeah.
Thank you.
And that's exactly what we need these tools for, right?
Yeah.
I have a question for Johannes. So it seems like these models are very much you focus a lot on the interior of the point cloud. So is there a point when you want to go back to the surfaces again?
Yeah, as I said before, I think it's always part the surface of the volumetric idea, because of course you have the outer shell as the representation of the actual object design, but also the interior structure is for us super important, because then we can actually design the inner logics in organizations more carefully for a sustainable use of materials and so on and so forth.
Okay, and I think, as we have seen in some of the other talks, the interior structure of the materials of the building bricks or so is becoming more and more important. We don't just pour concrete into a shell, but we have structure in the concrete to save material. So, are there any more questions? Anything else? Yeah, over there, Simon. I will hand the microphone to Simon, and then there's one at the back as well.
Oh, okay.
So, Michael, this is actually a question to you. Every time I see your symbol showing the connections between the people, a different set of links are missing. Is it because there are people who aren't getting on?
Okay, so this is actually, so there's two, there was one, I call this the connection star. So the first one was for our original proposal, where we had a number of interactions that we envisioned. We didn't have interactions between all of these 8 sub-projects, but now in the second phase, we came to realize that there's even many more interactions that we can have. For example, I mean, that we as lighting or as computer graphics people, we originally thought we will talk to the geometry people, but now we see that we can also talk to the structural engineers, because they want to do translucent materials, and then we can help them simulate the light, and also talk to the haptics people and so on, and to the material experimentation people, because they want to see how the new materials they create, how they will look like, and how the light transport can be simulated. So in the end, it's almost a complete. It's not everything is complete, but it's almost complete in the end. Yeah. But the difference is first phase and second phase. And there was a question at the back.
Yes, my question is also for Johannes. When printing the point clouds, my question is this a stock G-code, or did you do any modifications to that? And also, how do you assume the volume that you need? Like when you have points close to each other, is there an increase or decrease in the volume that you are printing?
So actually, I recently joined 1 year ago the research, and we started once actually trying to use the techniques we developed so far, but of course we have to develop a bit steps further how to actually hacking the code of printing of the toolpath. So we have nowadays, so far, a mixture of the classic method of layered structures, but just looking at the individual points with different kind of distributions and amount of material use. Yeah.
Okay, any final questions? Any final question? I don't see any. So this is the heart of our SFB. So it's more like one part of the heart. The other PhD students, some of the others have presented last year's, and more PhD students will present next year. So I hope you will come back next year. And now let's give them a big hand for their great presentations again.
Congratulations.